Okay. If a vector space has got an inner product defined on it, then it is actually called an inner product space, which in a very general case of infinite dimensional vector spaces is also called, under some condition, Hilbert space. By the way, there was a great mathematician in early part of 19th century, last century, David Hilbert. He used to work, he developed that kind of framework and worked extensively on that. His name, Hilbert space. We will call it inner product space. Okay. So, you are given V an inner product space over complex field C, or in general real field, in general complex, or it could be real also. Okay. I am taking complex field, and it is finite dimensional. It is given dimension V is equal to P. P is, that means finite dimensional vector space, P dimension, fine. Then consider, let W be a subspace. This is only a notation for subset. W be a subset, actually W is a subspace. It could be this with, I mean, it could be this also general form, the W equal to V or W is a proper subset of V, both, but then for the time being I am considering proper subset only. Okay, but this is a subspace. So, W I am writing this way, W is a subspace of V, it is not only a subset, it is given W is a subspace of V. Then for all V vector element of V, and this V could be within W or outside W, but part of V. You understand? When I say for all V element of capital V, V could be either within W or outside W, means outside W, but within capital V. Then for all V, I am writing for all, actually it is, I should write for each, but there is no this thing notation for each. So, essentially I mean for each V element of V, for every V there exists a unique, remember unique, there exists an unique, both existence and uniqueness I need to prove. A unique vector W, this is a vector element of W. So, given V you get only one W. Okay. In that sense, it exists and you get one, but it is unique. What is this W? It is called orthogonal projection of V on W space. So that it means what? I give a name, I am telling you given a V there is a unique W, and I give it a name, but what is this W? So that V minus W, this vector is orthogonal to the space W. Okay. This is the notation, this vector is orthogonal to the space W. You can call it an error vector or whatever, this is orthogonal to the space W. That means, for any, if you pick up any guy from W, take the inner product between that and V minus W, this vector, take any x element of W, V minus W comma x inner product will be 0 for any x element of W. This is what it means. It is unique, and then it has some property, we will come to that. This is a crucial thing in our adaptive filter course actually, this projection thing. I wanted to arrive at this and its property and other things. For that only I developed all that vector space and dimension, basis, orthogonality and all those things. Okay. Projection is the key thing. Because I told you qualitatively earlier that linear estimation is nothing but the problem of finding an orthogonal projection. Okay, but in the context of optical filtering, but that time I was using analogy of 3D space and all those things, not properly that mathematics. But that time I also made a statement that I will come back to that this and make a proper mathematical treatment, give a mathematical treatment to that. Okay, that is what it is now. Okay, so first I will prove uniqueness. Suppose it exists. How it exists? We will see later. It is very easy. Suppose it exists, then given a V there is only one W. You cannot have W1 and W2 for, so that in both cases V minus W1 also orthogonal to capital W, V minus W2 also orthogonal to capital W. If that be, W1 and W2 has to be same. That is unique. That is, suppose there exists W1 W2 element of W, so that V minus W1 orthogonal to W, V minus W2 orthogonal to W. Then I will prove that there is no other way but W1 and W2, these two have to be same. There is this property that the error will be orthogonal to this capital W, this is possible only for one small w, this W vector belonging to capital W. You can already in your mind imagine that, visualize the thing in a 3-dimensional vector space, that geometrical vector space. Give it a vector, you are projecting, means taking a perpendicular on a plane or whatever, you hit a point and that point vector is a projection, you can have only one, you can have two such, so that the error is still orthogonal to the, this perpendicular to the plane. You understood what I am saying in your, okay, I will come back to that figure later, or maybe here only. What I am saying is this, suppose you have got W is a space spanned by these two vectors, that is the plane, and there is your one vector V. This V, if you take a perpendicular, then V minus this vector is this we will call W vector, this is your V vector, V minus W, this is V minus W, and since I have taken to be 90 degree, V minus W is orthogonal to anybody, any fellow in this plane in the space spanned by these two, isn't it? But in this process, can you get more than one such projection vector? You cannot get only one, isn't it? If you call this W, you cannot get W1 and W2 two such vectors, so that for both of them V minus W1 having 90 degree, V minus W2 also having 90 degree, that is not possible from your elementary geometry, isn't it? But this is only visually it is coming, actually the mathematical thing is here. Using those very elementary axioms, and mind you, when I am proceeding, I am not using any angle, any meaning of the vectors. I am only using the basic notions of vector addition, scalar multiplication, and those few things about inner product, orthogonality and all that. I am not using any notion of angle, nothing. Okay, so whatever you prove here, that is the most general thing. Here visually it is obvious that two such projections are not possible which hold 90 degree angle with the tip of the vector. But mathematically the reason is here, which follows that suppose indeed it is true, then I will show that W1 and W2 has to be same, have to be same. That means if I take you gave me two things, that W1 and W2, and suppose they are not same, but still they hold the property, orthogonality property. Then I say fine, if that be so, let me take the difference between these two projections, if at all two different projections exist, and take the norm square. Norm square means inner product with itself. Okay. But this W1 W2 I can always write as V minus W2 minus V minus W1, and this is W1 minus W2 as it is. Now, W1 belongs to capital W, W2 belongs to capital W. So, W1 minus W2 belongs to capital W, and this is the inner product. I can take out this component first. This inner product can be separated into two inner product, one with this. What will that be? That has to be 0, because V minus W2 orthogonal to capital W, but W1 minus W2 belongs to W, because both W1 and W2 belong to W. So, that inner product will be 0 minus this one, inner product between this and this, V minus W1 and W1 minus 2, by the same reason that is also 0, isn't it, because V minus W1 is orthogonal to the entire subspace W, and W1 minus W2 belong to W. So, then this is equal to 0, is that understood? If norm square is 0, there is only possibility that the vector has to be 0 vector by your axioms. So, that means this is possible only when W 1 minus W 2 is 0, which means W 1 equal to W 2. Okay. So, if it exists, it is unique. Implies unique. No two such W's exist. So, that the V minus the W is orthogonal to the subspace W. Okay. And then comes another thing which is basically generalized version of Pythagoras theorem here. That is, I will show, and anybody in fact now knowing Pythagoras you also can show that suppose you have proved me okay fine that V can be orthogonally projected, you get only unique W. But suppose I take up any other vector, say W prime also from the subspace, and I measure the two error vector. One is V minus W when W is the orthogonal projection like this, and I pick up another vector, say this is W prime, I take this error also. So, this is one error, this is one error, these two I compare who has the higher norm. And Pythagoras will come up and will say this norm is higher than this. That means, orthogonal projection is such unique vector, so that the difference between the vector being projected and that vector is orthogonal to the plane, to the space, and that has the minimum norm square. That is, you take any other arbitrary fellow in the space, find a difference between V and that fellow and take the difference vector and find its norm square, that will always be larger than the one when you do the same with the orthogonal projection of V on the space. That is why orthogonal projection is so important to us, because it gives us that error which has minimum norm square or minimum norm. That is why projection is the best estimate of V when I am standing in or I am situated in W space. Sitting in W space, the best estimate of V will be the orthogonal projection of V on W, because other W prime I take, I find the error between V and W prime, it will have larger norm than between V and its projection, orthogonal projection. Whenever I say projection, orthogonal projection. Okay, it is very easy to prove this. You have to find out the norm square of this vector. Okay, that is any arbitrary W prime and V minus W prime is this vector. Find the norm square of that. That norm square will be what? You from this point you connect this point. This angle is 90 degree. This norm square will be square of this plus square of this, Pythagoras, and therefore, norm square of this norm square will be larger than the norm square here, as long as these 2 points are different, isn't it? The Pythagoras will be proved very easily, and again you see using our basic axioms only I arrive at the Pythagoras thing. I am not using any geometry, any angle and all that in all this proof. This is only for mental clarity. Okay. Here, say I am taking a V minus W prime, arbitrary W prime, and norm square of that. That will be what? V minus W prime I can write as this is the norm square of V minus W minus V minus W prime minus this V minus sorry. This will be very simple thing. This vector is nothing but summation of these two vectors. That is what I am writing. If you reverse the sign W minus W prime, it becomes sum. That is only thing, isn't it? But actually, algebraically, I am just writing V minus W prime like this. V minus W, where W is the orthogonal projection of V on W. W is capital W, and this is the difference. and inner norm square means inner product with itself, isn't it? This with itself. So, there will be if you expand it, there will be 4 inner products, this minus this, again this minus this. Direct terms will be V minus W with itself first, that is this one, and another term will be this with itself, and 2 cross terms. Cross terms will be 0, because V minus W, W is the orthogonal projection. So, V minus W is orthogonal to anybody in capital W, and this is lying in capital W, this difference, because both each of them lies in capital W, isn't it? W prime lies in capital W, from there only I took W prime, so does W. So, difference lies in capital W. So, this vector is orthogonal to this vector. So, cross terms will be 0, isn't it? So, this is the inner Pythagoras thing you see, hypotenuse and 2 sides, and this is the orthogonal projection. So, this is the error for when I am orthogonally projecting V on W, finding the projection, taking that error. So, that error norm square is always smaller than the error when you are not orthogonally projecting, but you are taking arbitrary W prime, because this is this plus this, until unless these two are same, this is a finite positive quantity, this is a positive quantity. So, total is larger than this, isn't it? This is that Pythagoras actually. That is why orthogonal projection is so important to us, because the corresponding error vector has the minimum norm square or minimum norm. So, error will have minimum norm means minimum strength. So, minimum norm solution, minimum error solution will be orthogonal projection. That is the best estimate of an external fellow V when I am staying in the subspace W. But then comes the question of existence. Everything I assume that there exists. If exists, then it is unique. Okay, then minimum norm, all those things I proved. But existence is the required. Existence is very easy. W is the subspace of capital V. V is an inner product space. There is inner product defined. So, obviously, by Gram-Schmidt procedure, I can have an orthogonal basis for any number of orthogonal basis or orthonormal, even orthogonal basis say for W. There is at least one orthogonal basis of W exists, and therefore, infinitely many exists. That we have proved the other day. See, I did not do all those things for fun. I did out of Gram-Schmidt with something in mind. So, there exists an orthogonal basis of W. Call that basis vectors to be alpha 1, alpha 2 up to dot 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 say alpha m, where m is less than p in this case, because I am taking a proper subspace. Okay. That suppose W is a span of m less than p. This is an orthogonal basis. So, capital W given, its one orthogonal basis given, because orthogonal basis exists, we have seen. Now, you have been given that external vector V. V could be in W, outside W, but V. Okay. To start with, you can assume V to be outside, because if V is already inside, you will see projection of V is V itself, because then only the error will be having minimum norm, and norm that will be error will be 0. If V is already in W, its projection will be V only. Projection is unique, and I find one vector V itself, so that the error vector has the minimum possible norm, that is 0. That means, that has to be the orthogonal projection, because orthogonal projection has the minimum norm, and projection is unique. So, that must be the orthogonal projection, isn't it? So, that is a very trivial case. That is why it is better you take small v to be outside W and in capital V, then it makes sense really. If you already have V within W, what is the point in estimating it? So, this is W given to me. Now, you have been given a V. Now, I say you form this vector as linear combination of these elements, some linear combination, so that you get something belonging to capital W after all. Orthogonal projection also belongs to capital W. So, that will be some linear combination of these orthogonal, but what kind of coefficients? I say, suppose you take the coefficients like this V comma alpha k k equal to 1 to m alpha k. That is V is an external vector, V is inner product. You take inner product of V along any of these vectors divided by the norm square, that is a coefficient multiplied by the corresponding vector. So, you get something belonging to capital W only, okay, it is a linear combination of these ones, but you can I will now show that the error between V and this vector, that is orthogonal to entire W, because that is orthogonal to each of the basis vectors. You understand my logic? I will find out V minus W error. If that error is orthogonal to each of them, then obviously orthogonal to any vector of W, because any vector is a linear combination of this, is not it? So, I will just show say V minus W say with alpha k is 0 for all k equal to 1 to m. Okay. I will show this, and it is not is very easy. You replace W by this. Okay. So, one inner product is between V and alpha k, write that separately, V and alpha k, another is minus with this, and remember all alphas are mutually orthogonal. So, in this inner product only one will survive, that is when you have got kth term in the summation, and then that time what, alpha k with alpha k, and this is a coefficient, this coefficient is what? This coefficient, please see one thing, only that will go out, but this is in the second coordinate, and I am dealing with complex case in general. This is the coefficient coming with what? Oh, this is coming with W. So, this will go out as it is, V alpha k by alpha k square, this is the coefficient that goes out, and then alpha k with itself. Alpha k with itself means again another norm. Obviously, this is the alpha k norm square, that and this cancels. Okay, these two cancels and these two are same. So, this is 0. Okay. So, then this is the actual form of that. It not only, so it shows it exists, uniqueness I have already proved, now it exists I have proved that such an orthogonal position exists, and you now got the specific form of the projection. That take any orthogonal basis, it could be any way, either these or in terms of beta 1 or whatever, but whatever you choose, take the inner product with the external vector V with them divided by the norm square, these are the coefficients by which you linearly combine the chosen basis. That will be always hitting at the same omega, same W, that is the projection. This is the form of the projection. Okay. No, I know that. Suppose I am throwing this thing, suppose I do this, I know because of linear algebra experience, I know, but suppose I do this, then it exists. Actually, this is you will see, each coefficient is what each some coefficient times alpha 1, some coefficient alpha 2, each is projection of V along alpha 1, projection of V along alpha 2, we will see later, and all them I am linearly combining. It comes easily from that thing. Anyway, now, so existence, uniqueness, everything done, I know the specific form also. Instead of V, you could also, instead of V, you can also, V is the external fellow. This coefficients are, I mean, you can also write as W comma alpha k. Simply, even if this is not there, W is something belonging to, this is a very general result, small w, forget about projection and all, small w is part of capital W, is not it? So, that means in terms of this basis, you have to write W as a linear combination of the basis, this we have already seen earlier, that you can always write W as a linear combination of them, each combiner coefficient will be W inner product with this by norm square. But that is same as this, even another from another angle you can see, V is what? V has got two components, one is W component, another is the error component, that is V is what? W plus V minus W. So, if each inner product you replace V by this W and V minus W, W with alpha k comes here, V minus W is orthogonal to entire W and therefore, to each of the alphas. So, that inner product goes, is it? So, instead of V you can also put W here, remember this. You will see many times I will be playing this kind of tricks when deriving some adaptive filters and all that later. I have not told about linear operation, isn't it? I have not told about linear operation. So, I should tell about something about linear operation. Suppose there is a vector space V 1, there is V 2, and I define a linear operation between V 1 to V 2. That means what? To each element in V 1, take each element, map it to some V 2, that is all. 1 to many not possible, you take every 1 to you will get only 1. Many to 1 possible, when many to 1 possible, then actually it is not an invertible operation, because you know out of anything here you can get more than one solutions. So, those are the invertible, but the 1 to many is not possible, many to 1 may be possible. This operator will be called linear operator if T linear, if for all alpha beta element of V 1, suppose you know T alpha, T alpha equal to say alpha prime belonging to V 2, T beta you call it beta prime belonging to V 2. Okay, individual mappings you know. Suppose instead of alpha beta I get C 1 alpha plus C 2 beta, T working on that. If T is linear, then this should be C 1 times T alpha plus C 2 times T beta, then it is linear. The if and only if. You understood what I am saying? No? It is a linear operation. That is, if instead of giving each vector separately, if you give a linear combination, T working dot on that is simply T you apply on the individual components and combine them. So, the superposition holds. There is linear operator. Orthogonal projection is a linear operation. That is, suppose you have got this space W, you have got a vector V which could be in W also. Both V and W they are in the bigger subspace of capital V. You are projecting orthogonally, you are getting a vector W. This is unique, it exists, everything I know. So, suppose W I write as an operation on V, that is working T working on V will give you W. It is an operation after all, linear or not linear I do not know. If instead of V I give another vector, I will get another projection. Capital W space is constant, you keep taking different values of V, different vectors, you keep getting different projections on W itself. So, that means projection is an operation which takes any choice of yours as V and gives you something in return from W, is not it? So, this is an operator relation, it takes V as its operand and gives you something from W as the output, it is an operation. I am saying this is linear, that is V 1 projected on that, suppose it is given is some W 1. This is trivially seen actually, T V 2 W 2. This V 1 is one vector, project you get W 1, V 2 another vector, project means subspace remains same. The subspace W I am not changing, V 1 is something I am projecting, I am getting W 1 out of W, V 2 is another fellow I am projecting, I am getting W 2 out of W. Then I am saying instead of V 1 V 2, if I have C 1 V 1 plus C 2 V 2, if I project this vector, I should get, this is my claim, I should get just this. So, T actually is kind of what? T is a projection, T is an operator V 2 W, is not it? T you see, What does T take? T takes any vector from the vector space V. That could be in W, that could be outside W, but it is always V. But what it gives you is always part of W only. So, it takes any fellow from V, any fellow from capital V, and gives you something from W. It is obviously you can see a many to one transformation, because W is contained in this. Suppose you take physically, if you take a line from here, you take another vector, these two projections will be same. Geometrically you can see, you can abstract, in abstract sense also you can see, it is a many to one transformation. There is to this vector, if I add anything along this error, any multiple of the error I add, I get this fellow. This vector plus error times some constant which is equal to this will give you this. That also will have the same projection, you can find out, So, it is a many to one transformation, but it is a linear transformation. My only thing is, only contention here is that it is a linear transformation. Then instead of V, suppose I start with V1, I get some kind of projection W1, another V2 I take, I get W2. Then instead of V1, V2, if I have a linear combination, C1 V1 plus C2 V2 outside, project that will be same as C1 W1 plus C2 W2. That is my claim, and that is very easily seen. I just make the fact that make use of the fact that projection is unique, and that projection error vector is orthogonal to the space, is it? So, question is if this be the vector V, is it that V minus this, that error is orthogonal to W? If that be, then obviously this is the projection of V on that, because projection is unique. If you call this vector V linear combination, then V minus this quantity, it is a vector in W, I do not know whether it is projection or not. So, I take error, if that error is orthogonal to capital W, then obviously it is a projection of V on capital W, because error is orthogonal and projection is unique, and that is very easily seen. V minus W for all x, take any x element of W, any vector of W, V minus W, sorry, V minus this quantity C1 W1, C2 W2 with x, x is any vector of W. Is it that this error is orthogonal to any vector of W? So, that is why I took any vector, any x. In fact, you can take x non-zero also, otherwise it becomes trivial. If you take x to 0, then irrespective of anything else, the inner product is always 0. Suppose I take non-zero x out of W, then is it that this error also is 0? Obviously, because what is V? V is C1 V1 plus C2 V2, put that here. So, you can write C1 times V1 minus W1 plus C2 times V2 minus W2 comma x, and now separate out V1 minus W1 with x would be 0, because W1 is given to be the projection of V1 on W, same with the other. So, inner product is 0, isn't it very trivially seen? So, it is a linear operator. If in otherwise you can see, if you see specific form, this was the form, isn't it? This was the form. Instead of V here, suppose you put resulting vector C1 V1 plus C2 V2, you can spread out C1 times inner product V1 with alpha k, C2 times inner product of V2 times alpha k. So, that way you get two different projections, because this is linear in the first coordinate. So, orthogonal projection is a linear operation. Remember this, two vectors projected on the same space, two vectors, so each one is projected on the same space, you call them W1 W2. Instead, if they are added and then projected, projection will be nothing but W1 plus W2. Okay, please understand this. Another important notion now I come to, that is direct sum decomposition of vector spaces. Again, I will come back to just vector space and not inner product, and then I will come to again the special case where vector space also has been given a inner product, and it is called inner product space. So, I can come back to the general notion of just abstract vector space, no inner product, nothing, and then I have direct sum decomposition. Suppose W1, W2 subspaces of V. Our starting V is same, V is a vector space, dimension P and all that over complex field C. W1, W2 are two subspaces such that there is no intersection, but they have to intersect at one point because there is a 0. 0 is common and unique. So, that giving that W1 intersect W2 only at the minimum possible thing, that is 0 vector, like x axis and this axis. This line is one subspace, this line is another subspace. This is spanned by this fellow, this is spanned by this fellow, isn't it? These two subspaces, they are subspaces of the 2D plane, 2D space. This plane or this, each is a subspace, but they intersect only at 0 vector at the origin, something like this. Then suppose alpha 1 dot dot say alpha r be a basis, no orthogonal basis here because no inner product, a basis of W 1 beta L, a basis of W 2. That means, this is a linearly independent set, this is a linearly independent set. Then my claim is, if you append the two, that also is a linearly independent set. Physically it is, because these fellows are outside the space spanned by this. So, if you append anybody, that forms a linearly independent set, but mathematically this set union this set is a linearly independent set. You can easily prove that suppose you form a combination like this, C 1 alpha 1 plus dot dot plus C r alpha r, and then D 1 beta 1 plus dot 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 plus D L beta L equal to 0 vector. If this is so, if this is possible that you have non-zero solutions for this, suppose you have non-zero solutions for this for all, that means this part is negative of this part. Okay. When you write this, okay, even otherwise, suppose you have given me this, I can always take this on the left hand side, right hand side, or take this on the right hand side. Okay. So, this summation is equal to this summation. Okay. But these two, that means this is something, but left hand side is a linear combination of alpha 1 to alpha 1, which it belongs to W 1, right hand side is a linear combination of beta 1 to beta L, so it belongs to W 2, but this is then some vector. If left hand side equal to right hand side, that means this would imply it will belong to then both W 1 and W 2. Left hand side belongs to W 1, right hand side belongs to W 2, we know. But if you can equate the two, that means they belong both to W 1 and W 2. But what belongs both to W 1 and W 2? Only 0. So, this part is a 0 vector. But if this is 0 vector, alpha 1 to alpha is a linearly independent set. So, only solution possible is C 1 to C r is 0. If this part is a 0 vector, beta 1 to beta is a linearly independent set. See the way I prove. These are the things you should develop, this mathematician's logic, or this is just logic, no kind of wishy-washy thing. Okay, no analogy, no this qualitative description. See the proof, the strictness, correctness of the proof. If this is so, this equal to this, what is the negative sign? That means, this is something which belongs to both W 1 and W 2. So, these and these have to be the 0 vector. If this is 0 vector, all the coefficients must be 0, because alpha 1 to alpha is linearly independent, same applies there. So, the only solution for this is C 1 to C r. These are the mathematical proof, C 1 to C r and D 1 to D L 0. Obviously, here you see, if you append the two, here this is spanned by only one fellow, here this is spanned by only four. These two fellows are linearly independent. If you append the two, they are linearly independent. If you consider the span of that union set, that will be a bigger vector space than W 1 and W 2. That will contain W 1 and contain W 2. If you call W to be span of and after all, this can be a basis because they are linearly independent. So, I am considering the span of this, dimension of the space will be L plus R. So, this W then I will write as this way. It is a direct sum, this is called direct sum, it is a direct sum of W 1 and W 2. It will mean what? Any vector of W please need this. This is key to the remaining part of the adaptive filter course, this direction decomposition thing. Earlier I said about orthogonal projection. Now very soon I will generalize, I will come to inner product space and I will take a very specific case of such direction decomposition called orthogonal decomposition. That is central to the entire adaptive filter theory that will come up. Everything is resting on that. This shall be denoting as this is notation only. What does it mean? Any vector of W is what? What does it mean? First W and W2, whenever you see they intersect only at 0. Direction means exclusion, mutual exclusion. So, intersect only at 0, 0 vector. And by this I am constructing a larger subspace which will take the basis of this and this as a union to form its own basis, which means any vector of W will be what? It is a linear combination of this, means there will be one component which is a combination of these fellows, another component combination of these fellows. So, in general any vector of W will be a summation of a vector from here and a vector from here. That is in general So, remember it is not set union of W1 W2, please understand that. This is not that okay, W1 is a subspace, W2 is a subspace, you are taking the union of that, please note this is the difference. It is not union of W1 and W2, you are adding, not appending, adding a component from here and here, it is not union. What is the direction of these two, this 2D plane? Because these two bases together, these two bases from together larger basis they span this, and therefore, any vector in this will be a linear combination of something from here and something from here, addition of some component from here, some in general. Of course, that will also take care of those cases where W2 is 0 and therefore, V is W1, that is only this axis. W is a W direction, means it will also contain W1, means those linear combinations for which the coefficients here are 0. So, all elements of W1 are part of W, because that time you are taking 0 element from here, 0 vector and some element from here adding, they are part of W, vice versa. All elements of W2 added with 0 from here give you the same element, that also is part of W. But when you are not adding with 0, you are basically adding something from here, something from there, non-zero. So, that is a typical form of element of W. Are you understanding? Please see, this is not set union of W1 and W2. If you do not, mind does not work, always think at it this. Whenever you get this sign, plus first tell your mind that this means they intersect only at 0. Next, I will take a basis of this, I will form a union of the basis. That union will span a space. That space is indicated by this fellow, this notation. So, there any vector will be having two components, summation of two components, addition of two components in general, a component coming from here, a component coming from here. Sometimes this component could be 0, so you get the component here only. So, basically that time you are taking that segment of W which is nothing but W1. Like this 2D plane, even in this 2D plane, if you are walking along this street, this line, you will be hitting upon only these vectors, they will not be present. Okay, they will be present only at origin. So, 0 plus this will give you this that way, or you can be on this line, 0 times this here plus this will give you the same thing back. Those are part of this, but in general any vector will be, if you write it, it will be having one component in this direction, one component in this direction. Okay. Now, suppose I have got an inner product defined on this. I am not considering any here there was no inner product, only linear independence dependence was basis. Okay. Now, I am giving one more this thing constraint, there is not constraint, one more thing, one more tool I am giving, that is it is not only so general, it has got also an additional thing given to it, that is inner product. So, when we have inner product, all those things of projection, orthogonality, everything comes up. There you see one thing, suppose W1 and W2 are such that it is given W1 is orthogonal to W. That means, any vector of W1, any vector of W2, they are mutually orthogonal. Then my claim is they intersect only at 0. Here I directly gave the W 1 W 2 such that they are intersecting at 0. Here I am saying that if they are orthogonal, then it shows that W 1 orthogonal to W 2 is nothing but 0. Can you prove this? It is very easy, 0 vector. One line proof. But how? What will you do? Suppose there is an alpha that belongs to this, that belongs to this space. That means alpha belongs to W 1 and alpha belongs to W 2, and W 1 and W 2 are orthogonal. So, that means alpha with itself is 0, because alpha belongs to W 1 also, alpha belongs to W 2 also. Please see the way I prove. There is no question with logical discrepancy anywhere. Alpha belongs to, only thing I am not writing the way it is written in book, most of the things I am conveying, because then that will waste too much of time. I am taking alpha belonging to this, that means alpha belongs to W 1, alpha belongs to W 2, alpha inner product must be 0, which means norm square of alpha 0, this means alpha 0. So, that means this has only one element, 0 vector. So, if W 1 are obviously, if you have this, if you have these two axes which are perpendicular to each other, they intersect, there is nothing common. This is proof, I am proving. This implies and then I prove it. This implies and then I prove that suppose I do not know this. So, I pick up any alpha from here, that alpha belongs to W 1 also, W 2 also, but W 1 W 2 are orthogonal. So, alpha with alpha must be 0, the norm square of alpha is 0, means alpha is 0. So, only fellow lying in the intersection is 0. Then if you take W 1 as the, say, for span of, I mean you have got say span of as before, alpha 1 dot 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 alpha what I took R, but this is given to me now not just any basis, orthogonal basis, because you have given me an inner product, why not orthogonal basis, orthonormal also, but I am taking general case of orthogonal. Both these are orthogonal basis. I am not writing it twice. These are orthogonal basis, this is orthogonal basis. Then I form a union of the two bases. Obviously, W 1 W 2 intersect at 0 we have proved as before, and now we form a basis, we form this. Is it an orthogonal set? If you take any two between here, they are mutually orthogonal, any two here orthogonal, but any alpha from here, beta from here, they are also orthogonal, because alphas belong to W 1, betas belong to W 2, and you have given me W 1 and W 2 are orthogonal. So, it is an orthogonal basis. If you consider the span of this, if you take the span of this and call it W, then this is orthogonal basis. Okay. This is orthogonal basis of W. Then this W I will write again as before. You see, even otherwise this is a basis, and I as before I can write it like this, because any vector of W will be linear combination of this, which means a component from this side, component from this side. I told you whenever you have this, imagine that they are intersecting at 0 and you are appending the two bases, you are forming a larger basis, span of that is what is meant by this. So, any vector of that span space, this space will be in general have two component, one from here, one from here. Here I have got the extra thing, to you can put this sign here to indicate that these two are intersecting at 0, because these two are mutually orthogonal, and therefore, you can take its orthogonal basis, orthogonal basis, orthogonal basis always like this. If you append them, you get a larger orthogonal basis, take the span of that, that is meant by this. Okay. Now, if you have a vector V, you have to project it, okay, on W. P W is an operator V. Please understand the notation. Actually, I suddenly brought this notation from somewhere. P W. What I mean is, I have told you that projection operation is a linear operation, isn't it? That time I was using the notation T T working on P. Instead of T, I bring in P. P is for projection, and projecting on whom? W. So, P W is an operator, it takes a V, P W V. So, what does it mean actually? There is a vector V, I am projecting it on the subspace W. But that formula I know, please understand that formula I know. What is the projection? It will be some, this is orthogonal basis. Please see, this total is orthogonal basis of W. So, V with inner product, V and we will have inner product between V and any of these fellow divided by norm square of the fellow multiplied by the corresponding fellow, summation. So, you will get one set from alphas, one set for beta. Let me write two summations. One say I equal to 1 to R, another say j equal to 1 to L, and this time you will have V comma alpha I by norm square alpha I. This is more general. Orthonormal, this will become 1, but I want to be more general, so that this expression show up, that is all. You can take orthonormal, that is no problem, very minor difference, times alpha I. Okay, if you take orthonormal, I will not deduct any marks, it is okay. But I do not have to give an impression that things are valid only for orthonormal basis. If I prove assuming orthonormality, it makes my life simple, this terms become 1, and this side again V with beta j divided by, this is the projection. But you see the beauty, what is this component? This is the projection of V only on W1, orthogonal projection of V on W1. What is this? Orthogonal projection of V on W2. That means, this is nothing but P W1 V plus P W2 V. This is possible only when the two subspaces W1 and W are mutually orthogonal. Please note this, this will play tremendous role in all the adaptive filter things we develop. Overall projection is a summation of the individual projections, where the two subspaces are mutually orthogonal. Okay. So, that is all for today. Next class, I will take you to again this random variables, and that time we will be dealing with inner product space or Hilbert space, you can say, of random variables, 0 bin random variables. There I will define again vector space involving them, what is meant by addition, subtraction, inner product, all that. Then I will get into what is called linear prediction, estimation, all those things. One filter will be developed in that process, one structure called lattice filters, linear prediction, lattice filters and all that. Finally, we will make it adaptive. Of course, otherwise not, because if they are orthogonal, then only I pick alpha 1 to alpha 1 and beta to beta, they become orthogonal basis. Since they are orthogonal basis, overall projection can be written like this, but I am picking up one component here, another component here. And now I tell you, without doing this, taking the explicit form, please take this as an exercise. Suppose you do not know this form really makes life easy. Suppose you do not know the form, you only know W1 and W2 are two orthogonal, two subspaces which are mutually orthogonal to each other. V projected on W1 was giving you small W1, V projected on W2 subspace was giving you small W2. Then proof directly that V projected on this thing will be summation of W1 plus W2 without taking recourse to this form. Thank you very much. Okay.